In section 3.3, we look at division of polynomials. We'll use long division and synthetic division. We'll talk about the remainder theorem and the factor theorem, and we'll see how that applies to finding zeros of polynomials. To start this section off, I want to review how we use division with integers from elementary school. So if you want to divide 251 by 3, then you start with 251, and then we use this division symbol, and then the 3 on the outside. And the first thing we do is we say 3 goes into 2, and it doesn't do that. So then we say 3 goes into 25 8 times, and then we multiply. So 8 times 3 is 24. And then we subtract, and 25 minus 24 is 1. Bring down the other 1. And then we repeat the process. And we say 3 goes into 11 3 times. 3 times 3 is 9. We subtract, and we have a 2. And then that's it for that number. And you could go into decimals and such, but here we're going to stop, and we're going to call this the remainder. So the remainder is 2. The divisor is 3, and that's what you're dividing by. 251 is called the dividend. That's what you're dividing into. And the 83 is called the quotient. Now, there are several ways to write the actual answer. I'm going to use this method here. I'm going to say it's 83 plus 2/3 instead of a mixed number, because I want you to understand that what you're actually doing with the 83 and the 2/3 is you're adding them together. That's going to become important when we talk about polynomials. And then it says, write the division statement. Well, the division statement is actually in this general form. It's the dividend is equal to the quotient multiplied by the divisor plus the remainder. And this is a statement of how you can rewrite the process of division as an equation in a single line here. So this would be 251 is equal to the quotient, 83, times the divisor, 3, plus the remainder, 2. And if you were to work out 83 times 3 plus 2, you would get 251. Now, how does that correspond to division of polynomials? Well, it's the same process. Example 2 says divide x squared plus 3x minus 7 by x plus 2, and then write the division statement. So I'm going to write it out again just like before. We'll have the divisor on the outside. On the inside, we'll have x squared plus 3x minus 7. And we look to see what goes into what, just like we did before. This time we're looking to see how many times x goes into x squared. In other words, what times x is equal to x squared? And the answer is x. Then we multiply, and we say x times x is x squared, and x times 2 is 2x. We have to use plus and minus and things like that, but essentially it's the same deal. You're just forming a new polynomial. Then we want to subtract, and the way we subtract is by go ahead and changing all of the signs to the opposite sign here. So we'll change both of those signs to negative. X squared minus x squared is 0. 3x minus 2x is x, and then we bring down the negative 7. Then we repeat the process, and we say x goes into x one time, so this is plus 1. 1 times x is x, and 1 times 2 is plus 2. change these signs again, because that's the subtraction step. X minus x cancels, and then we have minus 9. It's at this point that we can stop. And just like before, you stopped when the number was smaller than the divisor. Here we stop when the degree of what's left is smaller than the degree of what we're dividing by. The degree of negative 9 is degree 0. The degree of x plus 2 is degree 1. Remember that the degree is the highest exponent in those polynomials. Then we can write this as plus negative 9 over x plus 2. Let's write out the division statement. So it would be the dividend, x squared plus 3x minus 7 is equal to the quotient, and I'm just going to use the quotient part that we had originally, x plus 1, times the divisor, x plus 2, and then you should do plus the remainder, but the remainder is negative, so I'm going to write minus 9. That's the division statement, and it shows you what you would get when you divide x squared plus 3x minus 7 by x plus 2, what is the quotient, and then what is the remainder. Let's look at synthetic division. Synthetic division is a way of performing division of polynomials without having to write all the variables down, and you just keep track of everything. Example 3 is divide x squared plus 3x minus 7 by x plus 2 using synthetic division. So it's the same problem as before. We should get the same answer. When you're dealing with synthetic division, you want to think of your divisor in terms of x minus c, and c is the number that you're going to put on the outside for division. Now in this case we have x plus 2, so I need to think of that as x minus, and then what number would make this equal? Well, it was plus 2 on the left, so I'm going to need minus negative 2 on the right. So my c is negative 2. The c goes on the outside. Then we're going to drop this down 2 lines and then go over. And now we place the coefficients. So that's 1x squared, so I have a 1. Then I have 3x, so it's a 3. And then a negative 7. So include the signs with everything. And now here's the process of synthetic division. We're going to bring down the first number. Then we multiply. Negative 2 times 1 is negative 2. And then we add. Now you may think that this is slightly different than before because we used to subtract, but we've already taken care of the negative by choosing x minus c, and then in this case x minus negative 2. So we just add these numbers together. 3 minus 2 is 1, and then we repeat until we get to the end. Negative 2 times 1 is negative 2, and then negative 7 minus negative 2 is negative 9. The negative 9 is going to be the remainder. And then this piece here forms the quotient. But you have to rewrite it back into a polynomial. If you start on the right side, this 1 right here represents a plus 1 constant. And then the next one is 1 times x. And then if there were more numbers, you would just do x squared and then x cubed, and you'd keep going until you found all the numbers in front of x's and x squareds and x cubes and such. So the quotient here is actually x plus 1. We'll simplify that. And the remainder is negative 9. So notice that you can only use synthetic division when what you're dividing by is linear in the form of x minus c. That has to be the divisor. And you can change the x minus c to x plus c by adjusting the signs and such. But you can't have 2x minus 3, for example. You can't have any quadratics or anything. Synthetic division only works on these linear type divisors. Example number 4. Divide x cubed minus 7x squared minus 3x plus 4 by x minus 5 using synthetic division. So we're going to have a 5 on the outside. And our coefficients are 1, negative 7, negative 3, and 4. Bring down the first number. It's a 1. And multiply. 5 times 1 is 5. Add. Negative 7 plus 5 is negative 2. 5 times negative 2 is negative 10. Add. Negative 3 minus 10 is negative 13. Multiply 5 times negative 13 is negative 65. And 4 minus 65 is negative 61. So the quotient is x squared minus 2x minus 13. And the remainder is negative 61. Next, let's look at the remainder theorem. The remainder theorem says if a polynomial f of x is divided by x minus c, then the remainder when you do this division is the same thing as evaluating the function at x equals c, known as f of c. So let's demonstrate that with example number 5. Let's let the polynomial f of x be equal to x to the fourth minus 2x cubed plus 5x squared minus 8x plus 9. In part A, use synthetic division to find the remainder when f of x is divided by 3. So using synthetic division, we would have 3, and then we'll put down the coefficients, 1, negative 2, 5, negative 8, and 9. And then we'll do synthetic division. Bring down the 1. 3 times 1 is 3. Add. 3 minus 2 is 1. Multiply. 3 times 1 is 3. Add 5 and 3 is 8. 3 times 8 is 24. 24 minus 8 is 16. And 16 times 3 is 48. Adding 9 and 48, we get 57. So the remainder when we do this division is 57. Now let's do part B, which is find the value of f of 3. So f of 3 would be equal to 3 to the fourth minus 2 times 3 cubed plus 5 times 3 squared minus 8 times 3 plus 9. So that would be 81 minus 54 plus 45 minus 24 plus 9. And if you add all those numbers together, you get 57. And those numbers are the same. And that's what the remainder theorem is telling us, is that if you want to find the remainder when you divide by an expression in the form of x minus a number, then that is the same thing as evaluating that number inside the polynomial. And so you can use those back and forth, however you want to do that. It turns out that doing synthetic division and coming up with the remainder actually gives us some more information. Let's take a look at the factor theorem. So the factor theorem says let f of x be a polynomial, and then it has two parts. The first part says if f of c is equal to 0, then the term x minus c is a factor of f of x. So let's dissect that. It says if f of c is equal to 0, well, that's just saying that c is a 0 of the polynomial f of x. So if c is a 0 of f, then x minus c is a factor of f of x. Well, saying that it's a factor means that it's one of the factors where we can break f apart. We can say f of x is equal to x minus c times another factor, q of x. I use q for quotient. Part 2 of the factor theorem is the exact opposite. It's the converse. And it says if x minus c is a factor of f of x, then f of c is equal to 0. So these go both ways. So if you want to be able to factor f, all you got to do is find its zeros. And if you know its zeros, then you know how to factor f. Example 6. Use the factor theorem to determine if x plus 3 is a factor of x cubed plus x squared minus 11x minus 15. So the rationale here would be the following. If f of negative 3 is equal to 0, then x plus 3, which is really just code for x minus negative 3, is a factor of this polynomial f of x. Go ahead and label this as f of x right here. And so we'll determine this piece by using the remainder theorem. You could just evaluate it and determine that, but we need more information eventually. So we'll go ahead and practice doing it this way. So we'll do negative 3 divides into the synthetic division 1, 1, negative 11, negative 15. So we bring down the 1. 1 times negative 3 is negative 3. 1 minus 3 is negative 2. Negative 3 times negative 2 is positive 6. Negative 11 plus 6 is negative 5. And then negative 3 times negative 5 is positive 15. That adds to the negative 15 to give 0. So f of negative 3 is equal to 0 because that is the remainder. And the remainder theorem guaranteed that this would be equal to the evaluation. Since that's equal to 0, the factor theorem then tells us that x plus 3 is a factor. And so you may be wondering, well, how does it work out to be a factor? Well, it turns out that x cubed plus x squared minus 11x minus 15 can be factored as this one factor, x plus 3, and the other factor comes from the quotient. We'll turn this quotient information back into a polynomial, and it'll be 1x squared minus 2x minus 5. Let's look at example number 7. Use the factor theorem to determine if x minus 5 is a factor of x cubed minus 3x squared minus 14x plus 23. So we know that x minus 5 is a factor if, let's call this one g. All right, so there's my g of x. If g of 5 is equal to 0. So we'll evaluate g of 5 by using the remainder theorem. So we'll have 5 go into the synthetic division, 1, negative 3, negative 14, and 23. Bring down the 1. 5 times 1 is 5. 5 minus 3 is 2. 2 times 5 is 10. Negative 14 minus 10, negative 14 plus 10 rather, is negative 4. Negative 4 times 5 is negative 20. And that has a remainder of 3. So g of 5 is equal to 3. Therefore, x minus 5 is not a factor. So if it's not a 0, because it says it's actually equal to 3, then that means the term that it came from was not a factor. Let's look at example number 8. Sketch the graph of f of x equal to x cubed minus 2x squared minus 15x plus 36 by finding the zeros with their multiplicity. And then we give you a little hint here. It says try x equals 3. So we'll start with x equals 3, and we'll do the synthetic division to see if we can reduce this down to its zeros. That'll help us to graph it. So let's bring down the 1. 1 times 3 is 3. 3 minus 2 is 1. 3 times 1 is 3. Negative 15 plus 3 is negative 12. 3 times negative 12 is negative 36. And that has a remainder of 0. So 3 did work. So x equals 3 is a 0. We don't know what its multiplicity is yet because we haven't found the other zeros. But we now know that x cubed minus 2x squared minus 15x plus 36 factors as x minus 3 from this factor of a 3, and reconstituting these numbers back into a polynomial, x squared plus x minus 12. I need to keep going to find the rest of the zeros. So I'm going to factor this leftover part, x squared plus x minus 12, when it's equal to 0. Since it's a quadratic and it does factor, it won't be too bad. We have x and x, and then we have 4 and 3 with a plus 4 and a minus 3. So that gives me x is equal to negative 4 and x is equal to 3. Now, you should notice that this x equals 3 and this original one x equals 3 from this synthetic division, those are different x equals 3s. X equals 3s. They're different ones. So that is going to be multiplicity 2. The way to think about this is that the original cubic factored into x minus 3, and then x plus 4, and then x minus 3 again, using this factorization right here. But that can be simplified to x minus 3 squared, because there's two terms, and then x plus 4. So the zeros of this polynomial are x equals 3 with multiplicity 2, and x equals negative 4 with multiplicity 1. Now recall what it means to be multiplicity even and multiplicity odd. If the multiplicity is even, that means when we hit that x coordinate on the x-axis as a 0, that it's just going to touch, and the graph is going to stay on the same side of the x-axis that it already was. When we have a multiplicity that is odd, like multiplicity 1, then the graph is going to cross through the x-axis to the other side. So let's draw a graph. We have x is equal to negative 4, and we have x is equal to 3. We could do the end behavior, and the end behavior for this one is down on the left, and then up on the right. So it's going to start low. It's going to come to x equals -4 and pass through. Then it's going to come back down to x equals 3. And it's going to touch it, but it's not going to cross over. And then it's going to go up forever on the right side. And that's the sketch of f of x. Finally, example number 9. Find the polynomial of degree 3 whose zeros are 2, the square root of 3, and the negative square root of 3. So if we want degree 3, that means it needs to be cubic. It means the highest power has to be x equals 3. And if we know that the zeros are 2, square root of 3, and negative square root of 3, then that means we also know the factors where these zeros came from. That would be x minus 2, x minus root 3, and then it would be x minus the negative square root of 3, which I'm just going to write as x plus the square root of 3. And then to find a polynomial that has these as factors, all I have to do is multiply them all together. So let's say that f of x is equal to x minus 2 times x minus the square root of 3 times x plus the square root of 3. I'm going to break this down into parts. And the first part I'm going to choose is to do these two because they are conjugate of each other. They have the same c values, it's just one's positive and one's negative. So let me do that first. So we'll do x minus the square root of 3 times x plus the square root of 3. They are the difference of two squares, and we know that that multiplies out to give me x squared, and then negative the square root of 3 squared, which is minus 3. So now I can take that, and my f of x is equal to x minus 2 times x squared minus 3. And now we multiply. X times x squared is x cubed. X squared times negative 2 is negative 2x squared. X times negative 3 is negative 3x. And negative 2 times negative 3 is positive 6. And that's the polynomial. Now you could have a multiplier where you just multiply all the coefficients by a number like a 3 or a 5 or whatever. But that's not required, and it doesn't change the zeros. So this is perfectly fine.